Hey there, and welcome to Raelene Math. In pre-calculus and calculus, we study functions, and one of the most important things to know about the function is what is the domain. The domain is a set of input values that makes the outputs defined. The output values are the y values. We call them the range. And so we want a function value to be real, single, and finite. And a failure for a value to be real is called non-real, like I, which is the square root of -1. Once upon a time, it was thought that this equation didn't have any solutions because there was no number that you could square to get equal to a negative number, like -1. And then the concept or the idea was invented from some imagination that we could have a number I, which is the square root of -1, and if we square it, we get -1. And so there are two roots to this, or two solutions to this equation, plus or minus I. Now, a failure for a value to be a single answer, like the solution to the equation 0y equal to 0, there are an infinite number of possibilities for y that you could multiply by 0 to get 0. And so this y value fails to be a single solution or a determined value. And so we say that y is indeterminate because there is not just one single solution. And so numbers like 0 over 0 are examples of indeterminate values. And lastly, we might consider a number that fails to be a finite number, such as when you have non-zero over 0. Because if you multiply through by the 0, we get 0y equal to 5. And there's no finite, reasonably sized number that you can multiply by 0 to get 5. Now, each of these possibilities leads to a different graphical case, and there are 4 different cases that we need to consider for the basic functions that prevent the function values, or the outputs, from being defined. Remember, defined is real, single, and finite. And so let's look at these 4 cases and a couple of examples. So the first case we will look at for exclusion from the domain is the fact that denominators cannot be 0. So if we have a function, f of x, which is some numerator over denominator, then the denominator can't be 0. Because if the denominator is 0, then we have one of two possibilities. We either have 0 over 0, or we have non-zero over 0. And the case of 0 over 0 is indeterminate. And the first 3 functions across the top are examples of functions that have an indeterminacy when x is equal to 0. So this first function, f of x is equal to x over x. And here, when x is 0, the y value is indeterminate. And so that's an indication that when x is 0, y is trying to be more than one value, more than one height. And so y could be any one of these heights because that would satisfy the equation 0y equals 0. And so we don't want y to be more than one output value for a single input value of x because that fails to be the definition of a function. So we exclude all y values, including the y value that the graph looks like it's going through, which is at a height of 1, and we have a hole. And so when we have an indeterminacy for the y value, we may have a hole in the graph. We may also have a jump, and here we have a jump discontinuity when x is equal to 0. And this is an example of a function which is the absolute value of x over x. And so when x is equal to 0, we also have 0 over 0 in indeterminacy. And the third kind of indeterminacy that leads to a discontinuity in the graph is an oscillating discontinuity. Now this function is f of x equals sine of 1 over x, and we have the possibility of a 0 in the denominator here. So in the case of sine of 1 over 0, this oscillation is showing that y is trying to take on more than one single y value. Let's look at this graph a little bit more closely. So if we type in y equals sine of 1 over x, and if we zoom in, we see that there's not just one single height. In fact, this graph is so dense as we zoom in. If we take a look at another graph with an oscillating discontinuity, we can zoom in on both of them, and it gets a little bit mind-blowing, actually, how dense these graphs are, and kind of pretty. So we can do that with a lot of graphs that have an oscillating behavior, like the tangent of 1 over x graph. And so here we're getting lots of other behaviors as well. We're getting lots of oscillations, and we have some weird behavior going on. And so anytime we have a 0 in the denominator of a function, we have some problems. Here's another type. This graph is maybe not one of the basic ones, but when we look at it, there seems to be a couple things going on. It looks like we have a jump, but if we zoom out a little bit, we see that on the left side of the y-axis, y seems to be approaching a height of 0, but then on the other side, y seems to be shooting up towards positive infinity. So here we have an example of a graph, jump, and something else, a vertical asymptote perhaps. And so now let's consider some other basic functions. Y equals 1 over x. The presence of that 1 in the numerator means that the numerator can never equal to 0. And so we have non-zero over 0. And in this case, the shape of the graph, the behavior or the feature that we're getting, is a vertical asymptote. It's also known as an infinite discontinuity. And so that's the next basic function that we have. I'll call this one g of x equal to 1 over x. And when we have x equal to 0, y is equal to non-zero over 0, which is infinite. And when a y value is infinite, y is shooting off to either positive or negative infinity at that x coordinate, and we have what is called a vertical asymptote. Now this vertical asymptote shows two different signs for y. Y is approaching negative infinity on one side of the vertical asymptote, and y approaches positive infinity on the other side. And so this is a vertical asymptote of odd behavior. Because this is a function with odd symmetry, that's an appropriate name. Here's another kind of function. G of x is equal to 1 over x squared. Also, we'll never get a 0 in the numerator. Even if x is equal to 0, we'll still get 1 over 0, which is infinite. But in this case, because of the exponent of 2 in the denominator, the y-coordinates are never negative, and so y can't shoot off to negative infinity. In this case, y only shoots up to positive infinity, whether from the right or the left side of the vertical asymptote. And so this is still a vertical asymptote, but it's a vertical asymptote of even behavior. And the even behavior is just an indication that we have the y-axis, which is a mirror or an axis of symmetry for the function, because the function has even symmetry. And so these are some cases of odd behavior, in particular discontinuous behavior, of functions whenever we have 0 in the denominator. Either we get 0 over 0, which is indeterminate, a failure for the y value to be a single height, or non-zero over 0, which is infinite, and a failure for the y value to be finite. So let's take a look at a couple of examples where we have fractions and therefore denominators. To determine the domain, we have to make the restriction that denominators cannot be 0. Now it's possible in this function that we can simplify a little bit. We could continue with this domain restriction and simply say that the denominator is x minus 3, which can't be 0, and solving that says that x cannot be equal to 3. And so we end up getting that the domain is all real numbers, excluding or taking away the single value of 3. But it is interesting to note that for this function, we could have factored the numerator and reduced, and we see that we have a common factor of x minus 3. Now, we can't just reduce the x minus 3 and say that the function is the same graph as x equal to 3. The reason for that is, the function of x plus 3. The reason is because x plus 3 is a polynomial graph, a line graph, and it has no domain restrictions. However, the original graph of f of x does. It has a problem when x is equal to 3. And so we could use this simplified reduced graph to come up with the graph of the original, as long as we carry over or consider the domain restriction that x is not equal to 3. And so this is an indication that we have a hole, and the hole in this graph is going to be located at 3 for the x-coordinate, and then if we substitute the x with the 3 here, we get 3 plus 3 is 6 for the y-coordinate. This is just an indication that the point 3, 6 would have been on the line y equals x plus 3, but we are removing that point because the original function has a problem with x equal to 3. So this is like the first case where we have a hole in the graph. Here's another function. K of x is equal to 2x minus 5 over x plus 1. We don't have a common factor here. We could try. We could factor 2 out of the top, but we would get x minus 5 over 2. and so there's no common factor with the denominator. So we simply state that denominators can't be 0. Now keep in mind that x is not the denominator. The denominator is the whole expression of x plus 1, and therefore x cannot equal to -1. And so we state that the domain is all reals except for -1. We might also write it using interval notation, where we exclude the -1 by using the union and open brackets. We could also use inequality notation, saying that x is less than -1 or x is greater than -1. But I think the simplest notation when we are excluding just a single value is to show that we are removing just one point from all reals. Okay, here's another exercise to determine the domain of this function. We won't go too much into the issue, but we do see that there's an outer function of sign and an inner function with a fraction. And so we know that denominators cannot be 0, which simply applies that x, which is the sole denominator in this fraction, can't equal to 0. So the domain is x contained in the reals, excluding the single value of 0. Now these curly brackets are used whenever we have just a simple set, a finite set of values that we want to exclude. If we wanted to exclude the numbers 1, 2, 3, 4 from the real number line, we would write x contained in the reals minus 1, 2, 3, 4. And that wouldn't take away any of the numbers in between 1 and 2. For example, 1.5 or 2.1 or 3.9 are still part of the domain. We're simply removing these 4 values. The next type of domain restriction is the fact that radicands of even roots cannot be negative. Now, a radicand is the expression or the quantity or the value underneath a square root or a cube root or any kind of root. But we are specifying that the radicands of even roots and not of odd roots cannot be negative. So here's a function, y equals the square root of x, and we can see that when x is equal to -4, for example, which is a vertical line, that there is no intersection between the two graphs. And so if we wanted to evaluate the square root of -4, it might be interesting to break it apart as a system of 2 equations where we have a blue graph, y equals the square root of x, and then the input of the square root is -4, so the input is x. So we're really looking for an intersection between the red and the blue curves. And what we're finding is that there is no point of intersection, which means that there is no value for y along this number line when x is equal to -4. Now this number line is a number line of real values for y. So if there is no y value that solves the equation or the intersection of these two graphs, then we say that there is no real solution. And so y is non-real, in this case, is consistent with having no graph. So unlike when we had indeterminate and we had a whole, jump, or oscillation, like up here, here y was indeterminate and we had a whole, jump, or oscillation, or when y was infinite and we had a vertical asymptote. Now in the case when y is non-real, we get no graph. So this is helpful for us to work with in other kinds of scenarios where we don't recognize if the number is non-real or infinite or indeterminate. In those cases, if we had a graph, we could work backwards from whether we have a whole, a jump, or no graph, for example, to say what the number is. We'll see an example coming up. So in this exercise, we want to find the domain of this function, and the domain says that radicands of even roots must be non-negative. So radicands of even roots being non-negative means greater than or equal to 0. So directly underneath this expression or these words here, I will put the radicand, which is the stuff under the square root, which is going to be 5 minus x squared. And so we can rearrange this to get 5 is greater than or equal to x squared, and I'm going to now write that in 2 different colors, and I'm going to express it as a system of 2 functions, a blue function, y equal to 5, and a red function, y equals x squared. I'm going to draw these 2 graphs, and I'm going to use the graphs to help me solve the inequality. From the colors that I've coded, I see that the blue 5 is greater than or equal to the x squared. And so the blue 5 is really representing a blue y value, and the x squared is representing a red height on a parabola graph. Okay, so then we've got these two graphs, and we see that they are intersecting in two places. We can solve for those intersection points at negative square root of 5 or positive square root of 5. And that's really creating three different regions for us to consider. Region 1, Region 2, and Region 3. Now in Region 1, we can see that the red graph is higher and the blue graph is lower. But according to this statement, we want the blue graph to be higher or equal to the red graph. And so the red graph is the higher, not the blue, so we don't want Region 1. Now, because we have this equal to, we are looking for points of intersection. So we want to include the x values that make the two graphs equal in height. So we do want to include negative root 5 as well as positive root 5. In Region 2, looking straight up and down, we see that the blue graph is higher and the red graph is lower. And that is consistent with what we are asked to find, or the condition that we are given to solve for x from the inequality. So we do want Region 2. In Region 3, the red graph is higher, which is not what we want. And so from here we can come up with our solution. For the set of x values that make the blue graph higher or the same height, intersecting the red graph, we end up getting that x is contained in the set from negative root 5 to positive root 5, including the endpoints. Well, one of the easiest ways to confirm the domain of a graph is to actually draw the graph. So if we take a look at the fourth root function, I'm going to write the fourth root function raised to the exponent of 1/4. And we should see that this function exists only between x equals negative square root of 5 and x equals positive square root of 5. And sure enough, that graph, if we zoom out a little bit, we can start to believe that the graph only does exist. The heights only do exist or are defined, which means single real finite y values between these two x values. Okay, so it looks like we got the right domain for that function. Okay, the next case of domain restrictions are for powers. Now, before we talk about how to solve these things, we need to make sure we know what a power is. And it's best to start the question or the conversation with an exponential function. So if we have an exponential function, y equals 2 to the x, a lot of people will read that as 2 to the power x, and they'll think that x is the power. But x is in fact the exponent, and the answer of 2 raised to the exponent of x is the power y. So for example, if you write 2 to the 1 is 2, 2 squared is 4, 2 cubed, or 2 to the exponent 3 is 8, 2 to the 4 is 16, and so on, the powers of 2 are not 1, 2, 3, 4, 5. The powers of 2 are 2, 4, 8, 16, 32. Now this is probably the biggest misuse of language that I hear consistently everywhere in the world, no matter who I talk to. People say that the powers are the 1, 2, 3, 4, 5s, but those numbers are the exponents. This isn't such a big issue really, unless we are going to come up with the inverse function, because then once we have a point on an original graph, like the point 2, 4 here, for example, when the exponent is 2, the power, the second power of 2 is 4, then we're going to come up with the inverse of that point over here. And the inverse is the mirror image through the line y equals x. And so when we do that, we get the point 4, 2. We swap the domain and the range. So now x represents the powers, and y represents the exponents. And so it gets really confusing if you're not comfortable with the new notation and the new function log base 2 of x to know if x represents the exponent or the power, if both the original x in red was both exponent and power. Are you with me still? I hope so. So the point is, we're talking about domain restrictions, which means input restrictions. And so if a power is to be an input, it's going to be the input of a log function. So powers are the inputs of log functions because they are the outputs of exponential functions. And powers must be positive. Now, to be positive means to be purely greater than 0, unlike radicands, which can be greater than or equal to 0. And the reason for that is kind of obvious. If you look to see what's happening here in this table of values, we keep multiplying 2 by a positive 2. And so the powers are going to be repeatedly multiplied, or products of positive answers, positive numbers. So if we're only multiplying positive by positive, the powers, these guys over here, will only ever be positive. Okay, let's take a look at an example. In exercise 9, we want to determine the domain of the function log base 2 of x squared minus x minus 6 all over x. So the restriction is that powers must be positive. And the power is the input of the logarithmic function. So the power is going to be x squared minus x minus 6 all over x, and that's going to be greater than 0. Now, we could solve this graphically if we know how to graph the rational function in blue, but we don't always have to come up with a graph, because what we're really trying to do is determine the sign of this function. Now, this function might be called some other function. Maybe it's not the whole f of x, but maybe we could call it g of x. And so g of x is some rational function. So it reminds me that maybe I should factor this. Now, I don't really need the whole graph. I just need to know what x values make the height of the g of x rational function positive. And so for that, I can use a sign chart. In my sign chart, I'm going to put all of the factors that I've gotten. I'm going to put all of the roots. So I've got a root of -2, I've got a root of 0, and I've got a root of 3. Now I'm going to put a dashed line at the root of 0 because it's in the denominator, and I know that denominators can't be 0. Therefore, x cannot be 0. So really, I should put a second condition here, and denominators can't be 0. And so from that, I have another statement, and x can't be 0. Okay, I'm going to move my sign chart over a little bit. And now I'm going to use faint lines for my other two factors because they are interesting. They're in the numerator, but if there's a 0 in the numerator, then the overall fraction is 0. But the overall fraction is my power, and powers can't be equal to 0. So in fact, while they're in the numerator and allowed to be equal to 0, the power is not allowed to be 0. So I'm going to have to make those dashed lines as well. So x is not allowed to equal -2 or 0 or 3. Now I'm going to fill in my sign chart by putting my factors, x plus 2, x, and x minus 3. And so hopefully you've seen some other ways to fill in sign charts. I'm thinking graphically here, and I can fill it in quite quickly. If you need to, you can make a table of values, plug some test points in, and work them out. So here, the expression g of x, which is a combination of two factors multiplied divided by x, gives me negative, then positive, then negative, then positive. And I know that I want g of x, this blue graph, to be positive or lie above the x-axis, and that's going to occur in this second region or in this fourth region. And so from here I get that my domain is x contained from -2 until 0, union 3 to infinity. And again, the best way to check this is to sketch the original function's graph. So here I'm going to go to my keypad and I'm going to pull up the inverse log functions, and so I'm going to get log base 2 of the fraction x squared minus x minus 6 all over x, and that's what y is equal to. And if I look here, zooming out a little bit, I see some vertical asymptotes. And so I've got the x equal to -2 to 0, as well as greater than 3. But it's interesting because it's telling me a couple of different behaviors. over here, when x is less than -2, let's take a picture of this. Let's make all of the vertical asymptotes in purple. We'll take a picture of this graph and we'll sketch on it over in the other view. So if we want to analyze this a little bit more, we see that we've got no graph occurring here, but we have y approaching -infinity or positive infinity. So it seems to suggest that x equal to -2 and x equal to 0 are vertical asymptotes of the function. Similarly, x equal to 3 is a vertical asymptote because y is infinite, approaching -infinity. But for the x values like -8, for example, an x value of -8 produces a y value that has no graph. So it would suggest that the original function, f of -8, where we have no graph, is non-real. Meanwhile, f of -2, or f of 0, or f of 3 correspond to vertical asymptotes, so these values are infinite. And so that's what I was talking about earlier when we have some strange graphical behavior. If we have no graph or a vertical asymptote, we can start to work backwards to see what the number is going to represent. So f of -8 for this function is non-real, but f of -2, f of 0, or f of 3 are infinite. Let's look at this one more way. Let's take a look at a graphing program. So I'm going to go to TI Inspire, and I'm going to define the function log base 2 of the fraction x squared minus x minus 6 all over x. And I'm going to call that function f of x equals. Well, it doesn't like all that. I'll copy it. F of x equals that function. Okay, so let's just go back to our domain, and we see that if x is equal to -1, we have a point on the graph. And a point on the graph is a perfectly well-defined y value, and so we should be getting a real single finite y value when we evaluate f of -1. And sure enough, we do. Now let's see what happens when we evaluate f of 0. Here it's saying non-real result. We've got a couple of different options. We see that from the graph, f of 0 is giving us a vertical asymptote on the left, but on the right there is no graph. So that's one of those weird kind of hybrid behaviors. So I guess f of 0 is non-real because of the no graph portion on the right-hand side. Okay, well let's take a look at f of -2. Maybe that will also say non-real because we have a no graph portion on the other side. Now this one says undefined, and here it means infinite. So it may be a limitation of the calculator, or there may be more to the mathematics that we haven't uncovered yet. Let's see what happens at f of 3. We also get undefined, which is suggesting, because it's not saying non-real result, this calculator probably means undefined to mean infinite. And what happens if we put -8 in after all? It's telling us non-real result again. And it's saying if we want to get some complex calculations, we can change the mode. So let's do that. Let's change the mode in our calculator. So we can go to Documents, and we can go to, not here, Settings and Status, and Document Settings. And if we go to real or complex mode, we can go to rectangular mode. And you'll notice it said rectangular or polar. It has everything to do with vectors. And so if we try this again, we end up getting a real number and an imaginary number. So indeed, f of -8 is non-real. And let's just see what happens if we have the inner function, g of x, defined. We're going to get x squared. I'm going to type it like this. So this is just the radicand part. X squared minus x minus 6 all over x, and g of -8 is a negative number. So what that means is when we take log base 2 of a negative number, all of that is -33 over 4. Log of a negative is non-real. But if we plug -2 into our radicand or our power function, g of -2, we're getting 0. So this is giving us some input if we have log of 0 or log of a negative. So let's just capture that. It's turning out that if we have a logarithm of a negative number, we get non-real, and that corresponds with no graph. Meanwhile, if we have logarithm of 0, we get infinite, and we have a vertical asymptote. So there's a lot going on in this question. Might be worth trying it again. Let's take a look at the last example, coming from the last type of undefined y-value and domain restriction. So here we have another case where we have to look at the graph first, because the fourth case is that the value of the hypotenuse cannot be exceeded in magnitude by either leg of the right triangle. So if we were to form a right triangle, we know that the largest side is the right angle. And opposite the largest side of a polygon is largest angle is the largest side. And so that largest side is called the hypotenuse. And we also have an altitude, which I'll call A, and we have a base, which I'll call B. And so we have some angles here, theta, and the complementary angle, pi by 2 minus theta. Now, by Pythagorean theorem, we can come up with a relationship that a squared plus b squared equals h squared. But the truth is, no matter how big a and b and the angles are, they will never be bigger than the hypotenuse. So that's what this is saying. But remember, this is a domain restriction, and so we need a domain of a function. We need an input involving the hypotenuse. Well, if we think about the sine function, y equal to sine x is a trig function, and the input is an angle, and the output, the ratio, involves opposite over hypotenuse. It involves the hypotenuse. But it's not a domain because the hypotenuse is in the output. So again, we need to reflect through the line y equals x to get the inverse graph. Now there's a whole other part to the story about the function sine x not being 1-to-1 and getting the inverse function by restricting the graph. That's a whole other video, but we restrict the graph from negative pi by 2, and when I say that graph, we restrict the sine graph from these angle values, and then we reflect. And when we do that, we get this blue sine inverse function. So just like we did with the exponential and log functions, in the trig functions, we're going to get ratio of opposite over hypotenuse on the red sine graph, and we're going to get x as an angle. But for the inverse, we are going to get that x is the opposite over hypotenuse ratio. It's an input now. Meanwhile, the y will represent the angle. And so when we have an inverse trig function, then we're going to get possibly some ratios involving the hypotenuse. Now, there's a trig function of tangent of the angle, which is the opposite over the adjacent, and it doesn't involve the hypotenuse at all. So it's not part of this domain restriction. Okay, let's take a look at an example. We want to determine the domain of g of x equal to sine inverse of 4x minus 1. So we know that the hypotenuse cannot be exceeded. So I'm going to leave it in words like that. But it can't be exceeded in magnitude by the opposite or the adjacent. So I'll write in magnitude by opposite or absolute value of adjacent. And so what we see here, g of x equals sine inverse of 4x minus 1, the 4x minus 1 is opposite over hypotenuse. And so I'm going to create this looking like a fraction, making it 4x minus 1 over 1. And so I'm going to take my verbal statement and I'm going to create an inequality for this. So the hypotenuse is going to be 1, and the magnitude of that is in absolute values. And the opposite is 4x minus 1, and the magnitude of that is in absolute values. And the hypotenuse cannot be exceeded means that the hypotenuse is going to be greater than or equal to in magnitude to the other side. And so I want to think of this graphically. So if I'm solving this graphically, the first thing I'm do is going to simplify as much as possible. Absolute value of 4x minus 1 is now less than or equal to 1. I also maybe want to do a little bit of algebra just to simplify this. I have 4 times x minus 1/4, which is less than or equal to 1. And by property of absolute values, I can make the absolute value of a product equal to the product of the two absolute values. So maybe rather than thinking of this graphically, I can think of this verbally, because I know about absolute value is distance. And so I have the absolute value of x minus 1/4 is less than or equal to 1/4. And so when I read this verbally, this says that the distance between, so absolute value for distance, and then the word between comes from the subtraction between x and 1/4. Now I'm going to give 2 1/4 here, is less than or equal to 1/4 spaces. So the purple 1/4 represents a distance. So I'm going to think of this on a number line, a one-dimensional graph. And I have a center of the blue 1/4 because I'm saying that x is less than or exactly 1/4 spaces away from the center. And so to be 1/4 spaces away from something sounds like I'm on a circle. So I'm going to draw a circle, and the circle will be a radius or a distance of 1/4. And if I go 1/4 to the right, then I'm at 1/4 plus 1/4, which is 2/4 or 1/2. And if I go 1/4 spaces to the left, I'm at 0. And so x can either be exactly 1/4 spaces away or fewer than 1/4 spaces away, which means that x can be any of the numbers on the boundaries of the circle or between, because this is an x-axis. And so here we get that the domain is x is, well, let me use inequality notation. 0 is less than or equal to x, which is less than or equal to 1/2. And so we should take a look at this graph as well. We are going to graph y equals arcsin, which in this program is typed in as a sine of 4x minus 1. And we see that we have a graph bounded between x equal to 0 and x equals 1/2. And so there you have it. If we know the basic ideas about the number values, and we know 4 conditions and how to solve the equations or inequalities, we can come up with the domain algebraically for almost any function. Thanks for checking out Raelene Math.